Hello, we'll be present the integrated circuit logic family for the subject of digital systems with reconfigurable logic. The agenda of the topics to be addressed in this presentation includes the following. 1. Integrated circuits terminology. 2. The 7400 family circuits. 3. Standard family TTL. 4. Integrated circuits digital CMOS. 5. CMOS BGT, BiCMOS, MOS, ECL, DTL, RTL characteristics. 6. The scale of integration.
Integrated circuits terminology. Let's start with some key terminology regarding integrated circuits or ICs. An integrated circuit is essentially a small semiconductor device that holds a large number of components like transistor, resistor, and capacitor. These ICs are what we refer to as the brains of the modern electronics, used in almost every electronic device. The chip refers to the IC itself, and the package is the external casing that protects this chip. Inside the package, the die is the actual silicon piece where the circuit is built. Finally, pinout refers to the configuration of external connections which allow the IC to interact with the external circuit. Understanding this term is crucial as we move forward. The 7400 family circuits. Next, we have the 7400 family of circuits, which is one of the most commonly used series of logic IC. These are based on transistor logic, or TTL, and include a variety of logic gates like AND, OR, NAND, and XOR. Some of the most well-known models include the 7400, which is a quad 2 inputs NAND gate, and the 7404, a hex inverter. This IC forms the foundation of many digital systems, from simple circuits to complex computing systems. For example, the 74138 is used for 3 to 8 decoding, which is common in memory and control applications.
Now, let's dive into the different types of standard TTL logic families. TTL, or transistor-transistor logic, is widely used in digital logic family based on bipolar transistors. TTL-L, or low-power TTL, focuses on reducing power consumption, but has lower performance. TTL-S use Schottky diodes, which allow faster switching speed compared to the standard TTL. TTL-AS, or Advanced Schottky, improves speed and reduces power compared to the previous versions. TTL-ALS combines Advanced Schottky technology with low power requirements, offering a balanced solution. TTL-F, or Fast TTL, is optimized for higher speed operation. TTL-AF, Advanced Fast, goes even further, delivering faster performance with low power consumption. Finally, the TTL-HCT, or high-speed CMOS TTL, is compatible with CMOS logic levels but maintains a high speed associated with the TTL. Understanding this variation is important when selecting components for different performance and power requirements.
Integrated Circuits Digital CMOS. We have CMOS, which stands for Complementary Metal Oxide Semiconductor. CMOS technology is commonly used in digital integrated circuits because of its low power consumption and high noise immunity. In contrast to TTL, CMOS is more power efficient, especially when in an idle state. While older CMOS chips were slower than TTL, modern CMOS technology has reached speeds comparable to TTL circuits. Another advantage of CMOS is its superior noise immunity, making it more reliable in environments with electrical interference. Due to these characteristics, CMOS is found in a wide range of devices, from microprocessors to sensors and radio frequency applications. Its efficiency and versatility make it the preferred choice in most modern electronics. Here are some of the characteristics of the following technologies. We have already discussed CMOS circuits, and now we will begin with BJT circuits. BJT, bipolar junction transistor. BJT technology is based on NPN and PNP transistor and is typically used for analog circuits and high-speed switching applications. BJTs are known for their high speed and gain, making them suitable for amplifiers and fast switching devices. However, they consume more power than CMOS circuits due to the need for a continuous current to maintain their state. The density of integrations is also lower than CMOS, but BJTs excels in high-performance analog applications. BJTs are often used in applications that require fast switching speeds but don't need the high integration densities that CMOS provides. BCMOS, bipolar complementary metal oxide semiconductor. BCMOS technology combines the best of both worlds, the high-speed capabilities of BJT transistors and the low power consumption of CMOS. By integrating both types of transistors, BCMOS circuits can achieve high speed while maintaining lower power consumption than pure BJT circuits. This hybrid approach is often used in mixed signal applications where both digital and analog functions are needed. BCMOS is commonly found in high-speed interfaces, RF circuits, and analog-digital converters. However, the cost of manufacturing BCMOS circuits is higher than either BJT or CMOS alone, which can be a disadvantage. MOS, metal oxide semiconductor. MOS technology, specifically metal oxide semiconductor field effect transistors, or MOSFETs, is another variant that operates with low static power consumption. Like CMOS, most circuits are widely used in digital and analog applications. Most circuits offer moderate speed and very high integration densities, making them ideal for applications like amplifiers, power electronics, and logic circuits. While their power consumption is low when idle, most circuits might not perform as well in extremely high-speed applications as other technologies like ECL or BJT. ECL, emitter-coupled logic. Emitter-coupled logic is a technology known for its extremely high-speed operation. It achieves this by avoiding the saturations of transistors, allowing for very fast switching. However, this speed comes at the cost of high power consumption. ECL circuits are power hungry because a constant current flows through the circuits regardless of switching activity. ECL is typically used in high-speed computing, telecommunications, and signal processing applications where speed is a critical factor. While ECL is the fastest logic family, it has low integration density and is not suitable for power-sensitive applications. DTL, diode transistor logic. DTL is an older technology that combines diodes and bipolar transistors to perform logic functions. It was one of the earliest forms of logic, but has largely been replaced by more efficient technologies like DTL and CMOS. DTL circuits have moderate power consumption but are lower than modern logic circuits like CMOS. The integration density of DTL is also much lower, making it unsuitable for high-performance applications today. DTL is now mostly obsolete, having been replaced by faster and more power-efficient technologies. RTL, Resistor Transistor Logic. RTL was one of the earliest forms of logic circuits using resistors and transistors to perform logic operations. RTL circuits consume a significant amount of power due to the resistors and are very slow compared to modern technologies. The integration density is also very low, which limits the complexity of circuits that can be built with RTL. While it was used in early computing systems, RTL has since been phased out in favor of more efficient technologies. Today, it is considered obsolete and is rarely, if ever, used in modern applications.
Finally, let's talk about the scale of integration, which refers to the number of transistors of a single integrated circuit. SSI stands for a small-scale integration, with a few gates or flip-flops per chip, usually fewer than 10 transistors. These were typical in the early digital systems. MSI, or medium-scale integration, includes hundreds of transistors. These are used for more complex functions like decoders or small memory units. LSI, or large-scale integration, significantly increases the transistors count to the thousands, and it's often found in microprocessors and memory devices. VLSI, or very large-scale integration, is the next step up, featuring millions of transistors on a single chip. Modern CPUs and FPGAs are typically examples. Finally, ULSI, or ultra-large-scale integration, refers to chips with an even higher number of transistors, and these are used in higher performance computing and mobile devices. As technology evolves, we are continually pushing the boundaries of integration, allowing